Welcome to Dreamy Science, where we explore the fascinating world of scientific wonder. Imagine for a moment looking up at the night sky. We see our moon, a familiar silver orb, hanging serenely above us. It's a constant, a sentinel in the darkness. But what if, as you gazed at that familiar moon, you noticed something else? A tiny, even smaller speck, circling our moon. A moon of a moon, a submoon, or as some delightfully call it, a moon. The idea itself sounds almost whimsical, like something out of a science fiction novel. But here's the thing that makes this more than just a fanciful thought experiment. The universe, in its infinite complexity, often hides truths stranger and more beautiful than anything we could invent. Could such a celestial nested doll actually exist? And if not, why not? What fundamental laws of physics, what unseen cosmic choreography prevents or permits such a layered dance? This isn't just about finding a new type of celestial body. This question, can moons have their own moons, delves into the very heart of orbital mechanics, gravitational stability, and the delicate balance of forces that sculpt our solar system. It forces us to confront the intricate ballet performed by every planet, moon and asteroid, each tugging and pulling on the others in a symphony of gravity. The answer isn't a simple yes or no, it's a journey into the profound elegance and brutal limitations of the cosmos. It's about understanding why some configurations are stable for billions of years, while others are ripped apart in a cosmic blink. It's about appreciating the exquisite precision required for anything to orbit anything else, and the fine line between a stable system and gravitational chaos. And as we explore this, you'll find that the science isn't just a collection of facts. It's a story, an unfolding drama written in the language of physics, revealing the hidden rules that govern everything from the smallest dust motes to the grandest galaxies. It's a story that I hope will fill your mind with such rich detail and interconnected understanding that your brain will find a deep, satisfying peace in its complexity. If you're enjoying this journey through the fascinating world of science, I'd love it if you'd hit that like button and subscribe to Dreamy Science so you don't miss future episodes. And I'm always curious. Drop a comment letting me know what city you're watching from and what time it is where you are. There's something special about knowing this exploration of scientific wonder is reaching people all over the world at all hours of the day and night, connecting us through a shared curiosity about the universe. Let's start with a thought experiment that seems deceptively simple. Imagine throwing a ball. You exert a force, it flies through the air, and then, inevitably, it falls to the ground. This, of course, is gravity at work. But now imagine throwing that ball so incredibly fast, with such immense power, that as it falls, the ground curves away beneath it at the exact same rate. It would never hit the ground. Instead, it would fall around the Earth, endlessly. This, in essence, is what an orbit is, a continuous state of falling but never quite hitting. It's a perpetual dance between forward momentum and the relentless pull of gravity. And this fundamental dance, this cosmic waltz, is the very first step in understanding why a moon of a moon is such a peculiar and perhaps impossible idea. Early section, building the foundation. Everyone understands at a basic level that gravity is what keeps us on Earth and what keeps the Earth orbiting the Sun. But let's delve into the specifics of what gravity is and how it orchestrates these grand celestial ballets. Isaac Newton, centuries ago, gave us the foundational understanding. Every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. That's a mouthful, but it boils down to two key ideas. The more massive two objects are, the stronger their gravitational pull on each other, and the further apart they are, the weaker that pull becomes, and it weakens surprisingly fast. Double the distance and the force of gravity drops to 1/4 of its original strength. This isn't just an abstract law. It's the invisible hand that shapes every solar system, every galaxy, and every cluster of galaxies. Our Earth, for instance, isn't simply stuck to the Sun. It's constantly accelerating towards the Sun due to its immense gravitational pull, but simultaneously it's moving sideways at an incredible speed, about 30 kilometers per second or 67,000 miles per hour. It's this precise balance between its forward motion, its inertia, and the Sun's gravitational tug that keeps Earth in its stable elliptical path. If Earth moved slower, it would spiral into the Sun. If it moved faster, it would escape into interstellar space. The orbital parameters are incredibly specific, a testament to billions of years of gravitational equilibrium. Now extend this concept to our Moon. The Moon is orbiting Earth under the same principles. It's constantly falling towards us, but its sideways velocity is just enough to keep it from crashing down. The Moon's average speed is about 1 kilometer per second or 2 to 8 miles per hour, as it traces its roughly circular path around Earth. This might seem straightforward, but here's where it starts to get interesting. Our Moon isn't just feeling Earth's gravity, it's also feeling the Sun's gravity. And Earth is also feeling the Moon's gravity. Every object in the cosmos is locked in a complex multi-body gravitational interaction, and it's these subtle, constant tugs that become crucial when we ask if a moon can have its own moon. Middle section. The deep dive. The stability of an orbit, whether it's Earth around the Sun or the Moon around Earth, depends on a delicate balance, as we've discussed. But what happens when you introduce a third significant body into the equation? Let's call our hypothetical moon of a moon a submoon. For this submoon to orbit a primary moon, like our moon, it would need to establish its own stable orbit around that moon. This means it would have to be close enough to the primary moon for the primary moon's gravity to dominate its motion, yet far enough away not to crash into it. It would also need sufficient tangential velocity to maintain that orbit. However, the primary moon itself is not a stationary point in space. It's already in orbit around a much larger body, in our case, Earth. This introduces a powerful, disruptive gravitational influence on our hypothetical submoon. The Earth's gravity would be constantly tugging on the submoon, trying to pull it away from its orbit around our moon. This is where the concept of a Hill sphere becomes incredibly important. The Hill sphere, or Roche lobe, is a region of space around a celestial body where its own gravity dominates the gravitational influence of a larger, more distant body it's orbiting. Think of it as a gravitational zone of influence. For our moon, its Hill sphere is the region where an object would predominantly orbit the moon, rather than directly orbiting the Earth. Outside this sphere, Earth's gravity would be stronger, and the object would likely be pulled into orbit around Earth, or flung off into space, or even crash into Earth. For our moon, which has a mass of about 1/1 that of Earth, its Hill sphere is relatively small. It extends out to a radius of about 60,000 kilometers, about 37,000 miles. This sounds like a lot, but consider the moon's own radius is about 1,000 kilometers. So the stable region for a submoon to orbit within the moon's Hill sphere is limited. Any submoon would have to orbit the moon well within this 60,000 kilometer boundary. But even within this region, the Earth's gravity is not absent. It's merely less dominant. It still exerts a significant tidal force, constantly stretching and pulling at everything within the moon's gravitational domain. Late section. Implications and wonder. The existence of a submoon, therefore, isn't just a matter of can it orbit, but can it orbit stably for geological timescales? The constant differential gravitational pull from Earth would make any submoon's orbit around our moon incredibly precarious. It would be like trying to balance a spinning top on a tightrope while someone is constantly jiggling the rope. The Earth's gravity would perturb the submoon's orbit, causing it to precess, to tilt, to become increasingly eccentric, until eventually it would either crash into the moon, be ejected into an orbit around Earth, or be flung out of the Earth-Moon system entirely. The intricate dance of three bodies is notoriously difficult to maintain in a stable long-term configuration. This is why, despite the vastness of the cosmos and the sheer number of moons we've discovered, we have yet to find a single natural submoon anywhere. It's a testament to the unforgiving nature of orbital mechanics. Transition. Bridge to next chapter. So, we've begun to see that while gravity allows for orbits, the stability of those orbits, especially in a three-body system, is a much tougher challenge. The Hill sphere provides a boundary, but it doesn't guarantee permanence. In our next chapter, we'll dive deeper into these destabilizing forces, exploring the powerful invisible hands of tidal forces and orbital resonances, and how they conspire to make the concept of a moon a truly rare, if not impossible, cosmic phenomenon. Welcome back, fellow cosmic explorers. We've just dipped our toes into the vast ocean of orbital mechanics, marveling at the delicate balance that keeps our familiar silver orb hanging serenely in the night sky. We talked about the Hill sphere, that invisible bubble where a moon's gravity holds sway over its own potential satellites. But as we discovered, even within that seemingly safe haven, Earth's colossal gravitational presence isn't just a distant hum. It's a constant, powerful whisper that can turn a potential moon's orbit into an incredibly precarious tightrope walk. Today we're going to pull back the curtain even further on this cosmic drama. We're going to meet the true architects of instability, the unseen forces that conspire against the very idea of a moon having its own moon. These are the relentless, invisible hands of the cosmos, tidal forces and orbital resonances. Get ready, because the universe is about to show us some truth stranger and more beautiful than fiction, revealing the profound elegance and brutal limitations of its laws. Imagine, if you will, our hypothetical submoon, bravely circling our moon. It's got its own little orbit, its own tiny gravitational pull. Sounds simple enough, right? But here's the thing. Our moon isn't just sitting still in space, it's hurtling around the Earth at an astonishing speed, constantly falling towards our planet, yet perpetually missing it. And as it does, Earth's gravity isn't just tugging at the moon as a whole, it's tugging differently on different parts of the moon, and crucially on our little submoon. This differential tugging is what we call a sun-tidal force, and it's a game changer. Think of it like if you hold a rubber band and pull it from both ends, it stretches. Now imagine Earth as one giant hand and the moon as a smaller hand. The Earth is pulling on the near side of the moon, the side facing Earth, with slightly more force than it's pulling on the moon's centre, and it's pulling on the far side of the moon with slightly less force than it's pulling on the centre. This creates a stretching effect, deforming the moon itself, causing the familiar bulges of ocean water that give us tides here on Earth. Now, apply this same principle to our tiny submoon. As it orbits the moon, it's constantly moving closer to and further from Earth. When it's on the side of the moon closest to Earth, Earth's gravity pulls it harder, than it pulls the moon itself. When it's on the side of the moon furthest from Earth, Earth's gravity pulls it less hard than it pulls the moon. And when it's on the sides of the moon, perpendicular to the Earth-Moon line, Earth's gravity pulls it in a way that tries to drag it away from the moon and towards Earth. This isn't a gentle caress, it's a relentless, varying gravitational stress. Earth's tidal forces are constantly trying to pull our submoon away from the moon, distorting its orbit, making it wobble and stretch. It's like trying to keep a tiny marble orbiting a bowling ball, while the bowling ball itself is on a roller coaster, and a giant magnet is constantly trying to yank the marble in different directions. The submoon's orbit, which might look stable on paper if you only considered the moon's gravity, becomes a chaotic mess under the influence of Earth's powerful tidal fields. These forces don't just destabilize, they can outright destroy. If a submoon were to get too close to its primary moon, the tidal forces could be so immense that they literally tear the smaller body apart, scattering its remnants into a ring of debris. We call this critical distance the Roche limit, and it's a stark reminder of the universe's unforgiving nature. While our hypothetical moon might not be close enough to be shredded immediately, these constant tidal nudges inject energy into its orbit, causing it to either spiral inward towards a collision with the moon, or spiral outward until it escapes the moon's gravitational grasp altogether and becomes a direct satellite of Earth. Either way, its tenure as a moon is doomed to be short-lived. But wait, there's another cosmic saboteur lurking in the shadows. Orbital resonances. This is where the universe reveals its musical side, its symphony of gravity. Imagine a child on a swing. If you push the swing randomly, it might wobble, but if you push it at just the right moment with the right rhythm, you can make it go higher and higher with very little effort. That's resonance. In the cosmos, orbital resonance occurs when the orbital periods of two celestial bodies are related by a simple ratio of small integers, say 1-2, 2-3, or 1-4. For example, if our submoon orbited the moon twice for every one orbit the moon completed around Earth, that would be a 2-1 resonance. When this happens, the gravitational tugs from the larger body, Earth in this case on the smaller body, the submoon, become synchronized. Instead of random perturbations that might cancel each other out over time, these gravitational nudges arrive at predictable regular intervals, always at the same point in the submoon's orbit. The effect is cumulative. Each synchronized tug acts like that perfectly timed push on the swing, amplifying the disturbance. Over millions of years, these repeated, rhythmic gravitational interactions can dramatically alter an orbit, making it more elliptical, changing its tilt, or even kicking the object out of its orbit entirely. For a submoon, a resonance with Earth's gravity could spell disaster. The Earth's gravitational field, though distant, would be constantly tuning the submoon's orbit, pushing it further and further from stability. Think of it as a cosmic game of billiards played on an uneven vibrating table. The moon is one ball, Earth is another, and our submoon is the smallest, most vulnerable one. The moon's movement around Earth creates a dynamic, ever-changing gravitational landscape for the submoon. If the submoon's period around the moon happens to align with a multiple or fraction of the moon's period around Earth, those periodic gravitational disturbances from Earth will not cancel out. Instead, they'll add up, pushing the submoon's orbit into chaos. It's an elegant, yet brutal form of orbital instability. This brings us squarely back to the infamous three-body problem. We briefly touched on it, but it deserves a deeper look. Isaac Newton, brilliant as he was, could solve the two-body problem with perfect mathematical precision, predicting the exact path of two objects orbiting each other under gravity. But add a third body, and the equations explode in complexity. There is no general analytical solution for the three-body problem that predicts the long-term behavior of all three objects. Their dance becomes a chaotic ballet, where small initial changes can lead to vastly different outcomes over time. For our Earth-Moon submoon system, we have three significant gravitational players. The Moon itself is already in a complex, perturbed orbit around Earth due to the Sun's gravity. Now, introduce a submoon, and its orbit around the Moon is being constantly influenced by both Earth and the Sun. This isn't just a slight wobble, it's a relentless gravitational tug-of-war, where the rules are constantly shifting. The submoon's stability isn't just about its speed and distance from the Moon, it's about its relationship to the Moon's relationship with Earth, and Earth's relationship with the Sun. It's a nested doll of gravitational complexity. So when we combine the relentless stretching and pulling of tidal forces with the amplifying, destabilizing rhythm of orbital resonances, and then layer that onto the inherent chaos of the three-body problem, we start to see why natural moonmoons are so incredibly rare. In fact, why we haven't found a single stable natural one anywhere in our solar system. The cosmos, in all its wondrous complexity, has set up a series of gravitational gauntlets that make the existence of a long-lived submoon almost impossible. The universe, it seems, prefers its celestial bodies to simplify their relationships. A single moon orbiting a planet is stable, a planet orbiting a star is stable, but introducing a third, significantly smaller body into an already dynamically active hierarchical system creates a fragile house of cards, constantly buffeted by unseen gravitational winds. Does this mean our dream of a moon is completely dashed? Are these laws so absolute that no exception could ever exist? Or are there cosmic loopholes, peculiar circumstances, or perhaps even artificial interventions that could defy these powerful forces? We've explored the gravitational limitations, the profound elegance of these cosmic rules. But what if we looked beyond our own familiar neighbourhood? What if we considered other kinds of moons, other kinds of planets, or even the very fabric of orbital mechanics in a different light? Join us next time on Dreamy Science as we venture into the realm of the truly theoretical, exploring the edge cases, the fleeting possibilities, and the ingenious ways humanity might one day attempt to write our own chapter in the cosmic story of nested moons. We'll ask, if nature won't give us moons, could we build one? And what would it take? The answers, as always, are bound to be out of this world. Welcome back to Dreamy Science, fellow cosmic explorers. If you've been with us, you know we've embarked on a fascinating, if somewhat challenging journey into the heart of orbital mechanics. We've unravelled the elegant yet brutal truths of gravity, charting the delicate balance that allows celestial bodies to dance in their cosmic waltz. We've seen how the invisible hand of gravity, while creating the stunning order of our solar system, also acts as a formidable saboteur, making the existence of a natural moon, a moon orbiting another moon, seem increasingly improbable, if not outright impossible, in our immediate cosmic neighbourhood. We've delved deep into the Hill sphere, that crucial gravitational dominion where a moon's pull holds sway against its planetary host. But even within that sphere, we discovered the relentless perturbations of tidal forces and the rhythmic amplifying shoves of orbital resonances. These forces, in their relentless cosmic choreography, conspire to destabilize any would-be moon, threatening to fling it into the cold vacuum of space, send it crashing into its lunar parent, or even tear it apart before it can truly begin its own orbit. So where does that leave us? Does the universe, in its infinite complexity, offer any loopholes? Are there specific rare conditions, some hidden cosmic nooks and crannies, where such a celestial nested doll could theoretically find a moment of peace, a fleeting dance of stability? And if nature is so stingy with moonmoons, what about us, with our insatiable curiosity and ever-advancing technology? Could human ingenuity defy these cosmic limitations? Let's explore these tantalizing possibilities in Chapter 3, Cosmic Loopholes and Human Ingenuity. You see, the universe, for all its stern adherence to the laws of physics, occasionally presents us with regions of surprising stability, even within a complex gravitational ballet. We call these pockets Lagrange points, named after the brilliant 18th century mathematician Joseph Louis Lagrange. Imagine three bodies, a very massive one like our Earth, a less massive one orbiting it like our Moon, and a third much smaller body. At certain specific points in this three-body system, the gravitational forces from the two larger bodies, combined with the centrifugal force of the smaller body's orbital motion, perfectly balance each other out. It's like finding the exact sweet spots where everything cancels out, creating a kind of gravitational equilibrium. There are 5 such points, creatively named L1 through L5. L1, L2 and L3 are generally unstable. Think of them like balancing a pencil on its tip. The slightest nudge sends it toppling. But L4 and L5? These are the interesting ones. They are located 60 degrees ahead of and 6 degrees behind the secondary body, our Moon in this case, in its orbit around the primary, Earth. These points are like gravitational valleys, stable regions where a smaller object can comfortably reside, orbiting the primary body Earth, in sync with the secondary Moon. For example, Earth has a collection of asteroids known as Trojan asteroids that are trapped in its L4 and L5 points relative to the Sun. Jupiter famously has thousands of them. So you might be wondering, could a moon find stability at one of these Earth-Moon Lagrange points? Could our hypothetical submoon settle into L4 or L5 of the Earth-Moon system? Here's where we need to be very precise with our definitions. A body at an Earth-Moon Lagrange point is primarily orbiting the Earth, not the Moon. It's co-orbital with the Moon, sharing its orbital path around Earth, but it is not orbiting the Moon itself. It wouldn't be a moon in the truest sense, as it wouldn't be bound solely to the Moon's gravity. It's a crucial distinction, isn't it? While Lagrange points offer fascinating examples of gravitational stability in a three-body system, they don't, unfortunately, provide a direct answer for a stable object orbiting the Moon. The forces at play there are still dominated by the Earth's immense pull, and any object at L4 or L5 of the Earth-Moon system is essentially just another Earth satellite, albeit a very specially placed one. So while these cosmic loopholes are incredibly intriguing and host their own fascinating celestial bodies, they don't seem to offer a natural sanctuary for a true moon orbiting our familiar silver orb. The fundamental problem of the Moon's relatively small hill sphere and Earth's perturbing influence remains. This brings us to our next, perhaps more audacious question. If nature says no, could human ingenuity say yes? Could we, with our ever-advancing technology and relentless drive to explore, create a stable moon? The idea of an artificial moon is where science fiction often gleefully steps in, but let's ground it in some scientific reality. If we were to attempt to place a small satellite, a human-made moon into orbit around our Moon, we would face all the same gravitational challenges that natural moons do, but with one key difference. We could actively fight them. We could build in systems for active station keeping. Imagine a tiny satellite, perhaps no larger than a car, with small thrusters constantly firing, making minute adjustments to its orbit. It would be like balancing that spinning top on a tightrope, but with a tiny intelligent hand constantly nudging it back into place. What would this entail? First, incredible precision in orbital insertion. We'd need to launch our moon into an orbit around the Moon that is as high as possible within the Moon's Hill sphere, yet still stable enough to avoid immediate ejection. This orbit would need to be carefully chosen to minimize the perturbing effects of Earth's gravity, perhaps by orienting it perpendicular to the Earth-Moon plane, or by finding a specific resonant orbit that paradoxically uses resonances to maintain stability rather than break it. But even with the most precise initial placement, the relentless gravitational tug-of-war would begin. Tidal forces would still try to stretch and distort its orbit. Earth's gravity would still try to pull it away. This is where active station keeping comes in. Our artificial moon would need onboard propulsion systems, burning precious fuel to make regular tiny orbital corrections. Sensors would constantly monitor its position and velocity, feeding data to an onboard computer that calculates the necessary thrusts to counteract the destabilizing forces. This isn't a trivial undertaking. Fuel is heavy, and every gram launched into space is incredibly expensive. A moon requiring constant thruster firings would quickly deplete its fuel reserves, rendering it a derelict piece of space junk. So engineers would need to design highly efficient propulsion systems, perhaps ion thrusters that use very little propellant over long periods, or even consider harnessing solar radiation pressure for subtle nudges. Beyond fuel, there are other challenges. The harsh radiation environment of space, the constant threat of micrometeoroid impacts, and the sheer cost of building, launching, and maintaining such a complex system. But the allure is undeniable. Imagine a scientific outpost, a small observatory, or even a unique communications relay orbiting our Moon, offering unparalleled views and data collection opportunities. Perhaps a future lunar resource extraction operation could use such a moon as a staging post or a local sensor platform. The possibilities from a human perspective are boundless. This kind of active intervention represents our species' drive to bend the universe to our will, to overcome the natural limitations with technology and ingenuity. It's a testament to our ambition, though it also underscores just how difficult nature makes it for moons to exist on their own. Now, before we wrap up this chapter, let's quickly touch upon something that often gets confused with moons: quasi-satellites, or temporary captures. These celestial phenomena are not true moons, but they do offer a glimpse into the dynamic, sometimes chaotic nature of gravitational interactions. A quasi-satellite, like some of Earth's own companions, appears to orbit its host from a certain perspective, but it is actually still fundamentally orbiting the primary body, the Sun in Earth's case. It essentially dances around the host, staying gravitationally close for extended periods, but never truly becoming a satellite of that host. For a moon, a temporary capture would involve a small asteroid or comet passing too close, getting briefly snared by the moon's gravity, executing a few unstable orbits, and then, inevitably, being ejected back into space or crashing into the moon. These are transient, fleeting encounters, like a brief, chaotic dance before being spun off into the void. They are not stable long-term companions, and they serve to further highlight the immense gravitational hurdles that any true, stable moon must overcome. They are the cosmic almost-rans, the near misses that underscore the profound elegance and brutal limitations of the cosmos. So while natural moons in our solar system appear to be a cosmic rarity, if not an impossibility, the human spirit, ever restless and inventive, continues to dream. We look for those cosmic loopholes, those clever arrangements of gravity that might, just might, allow for such a phenomenon. And when nature closes those doors, we ponder how our own hands, guided by science and engineering, might pry them open. The question of moonmoons forces us to confront the profound interconnectedness of everything in the cosmos, the symphony of gravity where every note, every pull, every push contributes to the grand unfolding drama written in the language of physics. It's a reminder that even in the vastness of space, the rules are strictly enforced. As we move forward, we'll continue to peer into the potential futures of space exploration and how understanding these fundamental principles informs our grandest ambitions. What else does the universe hold that might surprise us, even if moonmoons remain elusive? Join us next time as we delve into the broader implications of these cosmic constraints and the wondrous possibilities that still await our discovery. We've journeyed deep into the intricate dance of celestial bodies, peeling back the layers of orbital mechanics, gravitational tugs and tidal forces. We've seen how challenging it is for a moon to hold on to its own moon, how the universe seems almost designed to prevent these delightful moonmoons from forming naturally, and how even human ingenuity faces monumental hurdles in creating them. The delicate balance required feels like trying to balance a spinning top on a tightrope during an earthquake. But here's the thing about the cosmos. It's vast, it's ancient, and it's full of surprises. Just because something is incredibly difficult doesn't mean it's impossible. So if we were to scour the universe, or even just our own solar system with a fine-tooth comb, what would be the absolute ideal conditions for a natural moon to exist, even if only fleetingly? What kind of cosmic loophole would we be looking for? Let's imagine a Goldilocks scenario. A confluence of rare events and perfect parameters where a moon might, just might, find a stable if temporary home. We're talking about a very specific set of circumstances, a celestial lottery where all the numbers hit. First, the primary moon, the one we want to have its own submoon, would need to be exceptionally large. Think of a moon the size of a small planet, like our own Earth's moon, or even bigger, like Jupiter's Ganymede or Saturn's Titan. The more massive the moon, the stronger its gravitational pull and the larger its Hill sphere, that crucial zone where its gravity can theoretically dominate over its parent planet. A bigger Hill sphere provides more elbow room, more gravitational real estate for a submoon to orbit. Second, this large primary moon would need to orbit its parent planet at a considerable distance. The farther it is from the planet, the weaker the planet's perturbing gravitational influence becomes within that moon's Hill sphere. Picture a wide, sweeping orbit, allowing the primary moon to maintain a more stable gravitational environment around itself, less subject to the constant disruptive tug-of-war from the planet. This distance acts like a buffer, insulating the primary moon's local gravitational domain. Third, the potential moon itself would need to be tiny. We're talking about something no bigger than a small asteroid, a mere pebble in cosmic terms. And crucially, it would need to orbit its primary moon incredibly closely. Why so close? Because even within a large distant moon's Hill sphere, the region of true long-term stability for a submoon is often a much smaller inner zone, nestled tight against its parent moon. The closer it orbits, the more strongly bound it is to its primary moon, and the harder it is for the planet's distant but persistent gravitational pull to wrench it away. We call this the submoon stability zone, a kind of gravitational sweet spot. It's like trying to keep a small child close to you in a crowded room. The tighter you hold their hand, the less likely they are to get pulled away by the crowd. Fourth, the entire system, the planet, the primary moon, and the potential submoon, would ideally need to have orbits that are as circular as possible, with very low eccentricity and inclination. Any deviation from a perfectly flat circular path introduces wobbles and perturbations, making the delicate balancing act even harder. Imagine the cosmic choreography needing to be perfectly rehearsed, with no missteps. A highly eccentric orbit for the primary moon, for instance, would mean its distance from the planet constantly changes, causing its hill sphere to expand and contract, which would be disastrous for any submoon trying to maintain a stable orbit within it. So could such a scenario exist in our solar system? We've explored the gas giant moons, Ganymede, Titan, Callisto. They are massive and orbit their planets at significant distances. They possess large hill spheres. Yet despite extensive observations, we haven't found any natural moonmoons around them. This tells us that even these seemingly ideal candidates still face insurmountable challenges from the combined forces of tidal effects and orbital resonances that we discussed in Chapter 2. The cosmic dance is just too complex, the symphony of gravity too dissonant for long-term stability. Perhaps we need to look beyond our solar system to exoplanetary systems. What if a planet orbited a binary star system, or was itself a free-floating rogue planet far from any star? The dynamics would be different, but the fundamental principles of the three-body problem would still apply. The quest for a natural moon pushes us to imagine the most extreme and rare configurations the universe might offer. It forces us to confront the profound elegance and brutal limitations of the cosmos. Even if a natural moon could form under these incredibly specific conditions, how long would it last? The universe operates on timescales that dwarf human comprehension. A configuration that might be stable for a few thousand years, a blink of an eye in cosmic history, would still be considered incredibly transient. The forces of gravity, even when seemingly balanced, are constantly at work, subtly nudging, pulling, and reshaping orbits over eons. An object might be temporarily captured, a quasi-satellite of a moon, but a truly stable, long-lasting moon, a permanent celestial nested doll, remains elusive. And why haven't we found one? The observational challenges are immense. A potential moon would be tiny, likely just kilometers across, orbiting a moon that is itself hundreds of thousands or even millions of kilometers from Earth. Detecting such a small, faint object against the backdrop of its much brighter parent moon, especially at vast interstellar distances, is like trying to spot a firefly orbiting a streetlight from across a city. Our current telescopic capabilities are incredible, but they have their limits, especially when searching for something so small and so close to another, larger body. But what if we could overcome these natural limitations? What if human ingenuity, driven by our insatiable curiosity and relentless ambition, found a way to not just maintain but to create and sustain a moon? We touched upon active station keeping in Chapter 3, the idea of constant thruster firings to correct an orbit. That's effective but fuel-intensive and expensive. Imagine a future where our technology is advanced to a point where active station keeping is no longer a constant struggle, but an integrated, self-sustaining process. Think about autonomous AI systems, constantly monitoring orbital parameters, making micro-adjustments with highly efficient, perhaps even solar-powered ion thrusters that sip fuel rather than guzzle it. Or perhaps we develop propulsion systems that don't rely on traditional chemical propellants at all, like advanced electromagnetic drives or even early forms of reactionless drives, if such physics ever prove possible. What if we could harness the very forces that destabilize orbits? Could we develop gravitational sails or tidal force compensators, hypothetical technologies that could subtly interact with the planet's gravitational field, using its own pull to stabilize a moon's orbit rather than disrupt it. This sounds like science fiction, and it is for now, but today's science fiction often becomes tomorrow's scientific endeavor. The purpose of such artificial moons would be profound. Imagine orbital space stations, not just around Earth, but around our moon. A moon could serve as a permanent scientific outpost, a stable platform for telescopes shielded from the lunar surface's dust and seismic activity. It could be a crucial stepping stone for resource extraction from the moon itself, acting as a low-gravity staging area for processing materials or building larger structures. Perhaps a moon could be a testbed for advanced propulsion systems, or even a precursor to truly independent space colonies. If we can master the art of creating and maintaining a stable artificial moon, we are essentially mastering the ultimate form of orbital control, an unprecedented level of command over the cosmic waltz. This would represent a monumental leap in our ability to not just explore, but to settle the solar system. The idea of a moon, whether natural or artificial, taps into something deeply human. Our desire to understand the fundamental rules of the universe, and perhaps to bend them to our will. It's about pushing the boundaries of what we believe is possible. The search for a moon in all its complexity is a metaphor for our broader scientific quest. To find the hidden truths, the truths stranger and more beautiful than we initially imagined, and to build new realities based on that understanding. As we continue to gaze up at the night sky, at our familiar silver orb hanging serenely, we now see it with new eyes. We see not just the moon, but the potential for an unseen, unheard cosmic choreography, an unfolding drama written in the language of physics. The question of whether moons can have their own moons is more than just an astronomical query. It's an invitation to contemplate the intricate interconnectedness of everything, and our own place in this grand, beautiful, and profoundly challenging universe. But our journey isn't over. We've considered the mechanics, the challenges, and the potential future. Now we must turn our attention to the implications of such a discovery, both scientific and philosophical. What would finding a natural moon mean for our understanding of planetary formation? And what would building an artificial one say about humanity's destiny among the stars? The next chapter awaits as we delve into the far-reaching echoes of this celestial curiosity. Here we are, at the precipice of understanding, having journeyed through the intricate dance of gravity, the delicate balance of orbits, and the relentless forces that shape our cosmic neighborhood. We've asked the question, can moons have their own moons, and delved deep into the physics that govern such a celestial nested doll. We've explored the brutal elegance of tidal forces, the destabilizing whispers of orbital resonances, and the ever-present chaos of the three-body problem. We even peered into a Goldilocks scenario, a perfect, almost mythical configuration that, to our knowledge, remains entirely hypothetical in the natural universe. We've even dared to dream of artificial moons, crafted by human ingenuity, defying nature's apparent decree. But now, as we stand here, gazing out at the vast, silent canvas of space, the question shifts subtly. It's no longer just if moons can exist, but what the profound absence of natural moons tells us about the universe itself. What cosmic truths are etched into the very fabric of space-time by this glaring lack of sub-satellites? Think of it this way. The universe is a grand architect, and gravity is its primary tool. Every planet, every star, every galaxy is a masterpiece of design, built according to immutable laws. And in this grand cosmic blueprint, it seems, the moon is a design that simply doesn't hold up under the stress tests of reality. It's not a flaw in the universe, it's a profound statement about its underlying structure. The very forces that allow moons to orbit planets and planets to orbit stars are the same forces that conspire against the stability of a moon orbiting a moon. It's a paradox of gravitational intimacy, a testament to the universe's elegant simplicity and its brutal, uncompromising efficiency. This isn't a story of failure, dear viewers, but a revelation. The difficulty, the near impossibility of natural moonmoons forces us to confront the true complexity of orbital mechanics. It pushes our understanding of the three-body problem, that notorious challenge to predict the long-term behavior of three gravitationally interacting bodies, to its absolute limits. We've learned that gravity isn't just a force of attraction, it's a sculptor, a choreographer, and sometimes a relentless destroyer of delicate ballets. It's an invisible hand that shapes not just what is, but what can be. The absence of natural moonmoons highlights the immense power of resonance and tidal forces. It tells us that even seemingly small gravitational nudges, when applied rhythmically over vast spans of cosmic time, can unravel the most carefully constructed orbits. Imagine a tiny whisper in a vast, echoing canyon. Over eons, that whisper can become a roar, rattling the very foundations of stability. This understanding doesn't just apply to theoretical moonmoons. It deepens our grasp of everything from the stability of planetary rings to the intricate dance of binary star systems. It's a universal lesson, written in the language of physics. So if our solar system, with its diverse array of moons, doesn't seem to harbour any natural moonmoons, what about beyond? What about the myriad exoplanets and their hypothetical exomoons swirling around distant stars we can only glimpse as pinpricks of light? Could there be a cosmic loophole, a unique set of circumstances in another stellar neighbourhood that allows for a stable moon-moon? Imagine an exomoon so incredibly massive, perhaps a super-Earth-size moon orbiting a gas giant, that its Hill sphere is vast enough to comfortably contain a smaller, distant submoon. Or perhaps an exomoon orbiting its parent planet at an extreme distance, minimizing the planet's tidal forces and allowing its own gravitational dominion to stretch unimpeded. We're talking about truly exotic scenarios, far removed from the familiar celestial architecture of our own solar system. Perhaps a moon in a very wide binary star system, where the influence of the second star could subtly alter the gravitational landscape, creating a stable niche. The same fundamental laws of gravity, tidal forces, and orbital mechanics would still apply, of course. But the parameters, the masses, the distances, the eccentricities might be so radically different that they could, in theory, shift the delicate balance. We are only just beginning to discover exomoons, and our current detection methods are still quite limited. The universe is unimaginably vast, and its capacity for wonder often exceeds our wildest imaginings. Could there be a celestial nested doll out there, patiently waiting to be discovered, a testament to the universe's infinite variations? It's a tantalizing thought, a dream for future telescopes and future generations of astronomers. And what of our own ambition, our human drive to create what nature seems to dim? The idea of artificial moonmoons, which we explored in Chapter 4, isn't just a technological challenge, it's a philosophical statement. It represents our species' relentless pursuit of understanding and control, our desire to not just observe the universe, but to participate in its creation, to push the boundaries of what is possible. Think of the scientific outposts, the research stations, the stepping stones for deeper space settlement that an artificial moon could represent. It's a testament to our ingenuity, our problem-solving prowess, and our unyielding curiosity. To build and maintain such a delicate celestial structure would require an unparalleled mastery of engineering, AI, and novel propulsion systems. It would be a grand ballet of technology, a constant, subtle dance against the very forces of nature that prevent their natural formation. It would be a symbol hanging in the sky of humanity's reach. Ultimately, the quest for moonmoons, whether natural or artificial, is a microcosm of our broader scientific journey. It began with a simple, almost childlike question, born of wonder. It led us down pathways of complex physics, revealing the profound elegance and brutal limitations of the cosmos. It showed us the interconnectedness of all things, how the smallest gravitational ripple can have cosmic consequences. The moon problem isn't about finding a simple yes or no answer. It's about the journey itself, the unraveling of cosmic secrets, the deepening of our understanding and the expansion of our perception of what is truly possible. It's about recognizing that the universe doesn't always conform to our neat intuitive expectations, and that the greatest lessons often lie in exploring the boundaries of what isn't there. So as we bring this exploration to a close, I want you to carry this sense of wonder with you. The universe is a place of profound beauty, intricate laws, and endless mysteries. The next time you look up at our familiar silver orb hanging serenely in the night sky, remember the unseen cosmic choreography, the symphony of gravity that holds it all together. And remember that even in the absence of a tiny moon orbiting our moon, there is a deep, satisfying peace to be found in understanding why. It's a testament to the enduring power of science and the insatiable human spirit that compels us to ask, what if? And then relentlessly to find out why not, or even perhaps one day how. This is the beauty of dreamy science, isn't it? To take a seemingly simple question and find within it an entire universe of interconnected knowledge. And the journey, my friends, is far from over. There are always more questions, always more wonders waiting to be unveiled. We've journeyed deep into the cosmic ballet, exploring the intricate pirouettes and grand sweeps of gravity that govern our own solar system. We've discovered the brutal elegance of its orbital mechanics, the uncompromising efficiency of tidal forces, and the silent, powerful whispers of resonance. Our conclusion for now remains: natural moonmoons, these celestial nested dolls, are an exquisite rarity, perhaps even a beautiful impossibility within our familiar cosmic neighborhood. The universe, we've learned, has a profound way of simplifying things, often through elimination. But here's the thing about the universe. It's vast. So vast, in fact, that even the most improbable scenarios can find a stage somewhere. We've only just begun to truly peer beyond our solar system to glimpse the bewildering diversity of exoplanetary systems orbiting stars light years away. And that, my friends, is where our moon quest takes its next thrilling turn. Could the conditions out there, in worlds we can barely imagine, finally tip the scales in favour of a natural moon? Could there be a cosmic loophole, a unique set of circumstances that allows for such a delicate dance to unfold? Imagine, if you will, a different kind of cosmic architecture. We've talked about the Hill sphere, that gravitational bubble where a moon's influence holds sway over its own potential satellites. In our solar system, even our largest moons like Jupiter's Ganymede or Saturn's Titan have Hill spheres that, while substantial, are still relatively small when compared to the overwhelming gravitational presence of their gargantuan gas giant parents. The primary planet's tidal forces stretch and pull, making any inner moon's orbit a precarious tightrope walk. But what if the primary moon itself were truly colossal? Picture a moon that's more akin to a planet in its own right, orbiting a gas giant that's perhaps even more massive than Jupiter. a super Jupiter, or even a brown dwarf, a failed star. If such a moon were, say, the size of Mars or even Earth, its Hill sphere would be significantly larger, offering a much more expansive and perhaps more stable gravitational haven for a submoon. Its own internal gravity would be strong enough to truly dominate a significant region of space around it. Then consider the distance. Our moons generally orbit their planets within a relatively close range. But what if a moon orbited its planet at an extreme distance, pushing the very boundaries of the planet's Hill sphere, yet still gravitationally bound? In such a scenario, the moon's own Hill sphere, while potentially distorted by the distant primary, could still be large enough and far enough removed from the planet's immediate gravitational harassment to allow for a stable moon-moon orbit. The tidal forces, while still present, would be significantly attenuated over such vast distances, giving our hypothetical moon-moon a much calmer ride. It's like moving from the choppy waters of a harbour to the calmer open sea, still subject to the ocean's currents, but less buffeted by the immediate shoreline. And what about the nature of the orbits themselves? We discussed the Goldilocks scenario of highly circular coplanar orbits. In the chaotic nurseries of exoplanetary systems, we've observed planets with wildly eccentric orbits, sometimes even retrograde paths. While this often spells instability, could it, in rare configurations, create a dynamic equilibrium where a moon-moon could find a stable niche? Perhaps a primary moon in an extremely wide, stable and perfectly circular orbit around an exoplanet, which itself orbits a star in a similarly tranquil fashion. The fewer gravitational perturbations, the better for our delicate nested system. We also need to consider the composition and density of these celestial bodies. A denser moon, for instance, might have a stronger gravitational pull for its size, potentially extending its Hill sphere effectively. Or a moon composed of materials that are less susceptible to tidal deformation could offer a more stable platform for a moon-moon. These are subtle factors, yes, but in the finely tuned symphony of gravity, every note matters. Now, detecting such systems, let alone confirming a moon-moon, is where our current technology truly faces its Everest. We are, after all, still in the early stages of confidently identifying exomoons themselves. Imagine the incredible challenge of finding a moon, orbiting a planet, orbiting a star, a cosmic onion, peeled layer by a painstaking layer. Our primary methods for exoplanet detection, like the transit method, observing a dip in starlight as a planet passes in front of its star, or radial velocity, detecting the wobble in a star caused by an orbiting planet's gravitational tug, are already pushing the limits of our instruments. To detect an exomoon, we're looking for a subtle secondary dip in the transit light curve, or a minute deviation in the planet's own wobble. It's like trying to spot a firefly orbiting a moth, which is orbiting an eagle, all against the blinding glare of the sun. The signals are incredibly faint, often buried in the noise. For an exomoon moon, the signal would be even more infinitesimally small, an almost imperceptible flutter in the light curve of an already tiny dip. It would require telescopes with unprecedented precision, observing over extremely long periods, and sophisticated algorithms to filter out all the cosmic static. Direct imaging, which allows us to actually see exoplanets, albeit as mere pixels, is even harder for exomoons, and for ex-moon-moons, it's currently the stuff of science fiction. The sheer distances involved, combined with the relative sizes and brightnesses of these objects, make it a truly monumental task. Yet our instruments are constantly improving. The James Webb Space Telescope, JWST, is already pushing boundaries, and future generations of space and ground-based observatories, perhaps equipped with advanced coronagraphs to block out starlight, or even entirely new detection principles, might just give us the tools we need. The dream of finding a natural moon out there, a testament to the universe's boundless creativity, continues to fuel our technological advancements. So are moons rare? Almost certainly, incredibly rare even. The specific Goldilocks conditions required a massive distant primary moon, perfectly circular orbits, minimal perturbations, seem to defy the general chaotic tendencies of gravitational systems. The universe, as we've seen, favours simplicity and efficiency, and complex nested orbital architectures are anything but simple. However, the sheer cosmic abundance of planetary systems plays a crucial role here. Our Milky Way galaxy alone is estimated to contain hundreds of billions of stars, many of which host multiple planets, and beyond our galaxy there are trillions upon trillions of other galaxies. If the probability of a natural moon existing around any given exoplanet is, let's say, 1 in a trillion, then given the sheer number of potential systems, the universe almost demands that at least a few must exist somewhere. It's a profound thought. Something almost impossible can become inevitable when scaled across the boundless canvas of the cosmos. This paradox reinforces the wonder of our scientific endeavour. We search not just for what's common, but for what's unique, for the outliers that challenge our understanding and expand our cosmic imagination. A moon, if ever discovered, would be a jewel in the crown of exoplanetary science, a living testament to the endless possibilities woven into the fabric of space-time. But what if nature, even across the vastness of the cosmos, consistently says no to natural moons? Does that mean our fascination with them ends? Absolutely not. For humanity, the absence of something often ignites an even fiercer drive to create it. If we can't find them, we will build them. We've already touched upon the idea of artificial moons, maintained by constant station-keeping and thrusters. In our present technological era, this is a monumental undertaking, fraught with challenges of fuel cost and the relentless wear and tear of the cosmic environment. But let's project ourselves into a future where our technological capabilities have grown exponentially, where we've truly begun to bend the universe to our will. Imagine advanced propulsion systems that make current rockets look like firecrackers. We're talking about fusion drives, perhaps even early forms of antimatter propulsion, or highly efficient solar sails that can harness stellar wind with unprecedented power. These wouldn't just be for getting to a moon, but for maintaining precise orbital positions with minimal energy expenditure over centuries or even millennia. Couple this with sophisticated artificial intelligence, not just AI for processing data, but for autonomous orbital maintenance. These AI systems could constantly monitor gravitational perturbations, anticipate potential instabilities, and make minute, precise adjustments to thrusters, or even deploy dynamic counterweights or electromagnetic fields to stabilize a moon's orbit. Imagine a self-correcting, self-repairing celestial mechanic endlessly fine-tuning the delicate balance. What would be the purpose of such a grand undertaking? The possibilities are as vast as space itself. Artificial moons could serve as unparalleled scientific outposts, providing unique vantage points for observing their primary moon, the host planet, and the distant star system with unprecedented detail. They could be vital staging points for deep space resource extraction, processing materials from the primary moon or asteroids and then launching them towards distant colonies. Perhaps most profoundly, artificial moons could become the ultimate space habitat. Imagine entire cities, self-contained biomes orbiting the natural moon, providing stable environments for human habitation and scientific research, Shielded from the harsh radiation of space by the primary moon itself, they would be true stepping stones to the stars, enabling humanity to expand its presence far beyond Earth and its immediate celestial neighbours. The dream of living in a celestial nested doll would move from whimsical thought experiment to engineered reality. So, our journey with Can Moons Have Their Own Moons brings us full circle. From the initial spark of curiosity to the deep dive into orbital mechanics, from the brutal truths of our solar system to the tantalizing possibilities of exoplanetary systems, and finally to the audacious dreams of human ingenuity. The absence of natural moonmoons in our immediate cosmic neighbourhood isn't a dead end for our inquiry. It's a profound lesson. It teaches us about the elegance and the uncompromising nature of physics. It underscores the immense power of gravity, not just as a force of attraction, but as a sculptor of order, and sometimes a relentless agent of chaos that prevents certain configurations from enduring. The universe, in its wisdom, often prefers simplicity, yet within that simplicity there is an infinite complexity waiting to be uncovered. Our search for moonmoons, whether natural or artificial, is a testament to the insatiable human spirit of exploration and creation. It is about pushing the boundaries of what we know, what we can observe, and what we can build. It's about understanding the symphony of gravity, appreciating its profound elegance, and perhaps, one day, learning to compose our own celestial melodies. As we conclude this exploration, remember that science isn't just about finding answers. It's about asking deeper questions, about marvelling at the universe's truths, even the ones that defy our initial hopes, and about being inspired to reach further, to build smarter, and to dream bigger. The cosmos is an endless source of wonder, and every question we ask, every theory we test, every observation we make, brings us closer to understanding the grand, unfolding drama written in the language of physics. And that, my friends, is a journey that never truly ends. We've journeyed together, haven't we? From a whimsical question about a moon, that delightful nested celestial body, to a deep dive into the profound elegance and brutal limitations of the cosmos. We've unravelled the invisible threads of gravity, danced through the complexities of orbital mechanics, and stared into the heart of the three-body problem, understanding why our solar system, with all its familiar wonders, seems to offer no natural home for such a creature. You might be thinking, well, if it's so improbable, why do we even bother? And that, my curious friends, is where the true heart of dreamy science lies. It's not just about finding answers, it's about the quest itself. It's about what the very act of asking, of searching, of imagining a moon reveals about the universe, and perhaps even more so, about ourselves. Because here's the thing, the absence of a natural moon in our neighbourhood isn't a defeat, it's a revelation. It speaks volumes about the universe's uncompromising efficiency, its elegant simplicity in orbital dynamics. It tells us that gravity, that unseen hand that shapes galaxies and dictates the paths of planets, is a far more precise and demanding architect than we might initially conceive. It's a cosmic truth, etched into the very fabric of space-time, that stable nested orbits under typical conditions are simply too fragile, too susceptible to the relentless tug-of-war between stellar giants and their smaller companions. But what do we gain from understanding this profound absence? Everything. Every no we encounter in science refines our understanding of yes. The search for moons, even if it yields no natural examples in our solar system, has pushed the boundaries of our gravitational models. It has forced us to scrutinize the delicate dance of celestial bodies with unprecedented precision, enhancing our ability to predict orbits, understand long-term stability, and even model the formation of planetary systems far beyond our own. We learn more about what is by understanding what isn't. It's like trying to find a specific pattern in a vast tapestry. Even if the pattern isn't there, you learn an immense amount about the threads, the weaving techniques, and the overall design simply by looking. And let's not forget the grand stage of exoplanetary systems. While our solar system might be a moon-moon free zone, the universe is vast, a cosmic kaleidoscope of possibilities. Could a moon-moon exist out there orbiting an exomoon, which in turn orbits an exoplanet, all dancing around a distant star? The theoretical conditions we outlined, a massive primary moon, a tiny close submoon, perfectly circular orbits, and a significant distance from the host planet, become a sort of cosmic treasure map. We know what to look for even if we don't yet know where. The very idea of an exomoon with its own submoon is a tantalizing prospect for astrobiologists. Imagine an exoplanet, a gas giant perhaps, orbiting its star in a distant, potentially habitable zone. And then imagine one of its moons, a rocky world potentially teeming with life. And that moon has its own tiny companion. This moon could be a crucial factor in the larger moon's habitability, perhaps stirring up tidal forces that generate internal heat, or even acting as a stable platform for a future advanced civilization to observe its home world. The existence of such a nested system would radically expand our understanding of planetary system architecture and the diverse pathways life might take. How would we even begin to find such a celestial nested doll light years away? This challenge too fuels innovation. We're talking about next-generation observatories, telescopes so powerful they can detect the minute gravitational wobbles of an exomoon as it's subtly perturbed by its own submoon. We're pushing the limits of direct imaging, trying to resolve a speck of light orbiting another speck of light, all against the blinding glare of a distant star. Techniques like highly precise transit timing variations, looking for tiny deviations in an exomoon's transit across its planet, which could be caused by an orbiting moon-moon, become our cosmic divining rods. It's a monumental task, requiring not just bigger mirrors, but entirely new ways of processing data, filtering noise, and discerning the faintest whispers of gravitational influence. It's a testament to our insatiable curiosity that we even conceive of such observational feats. But the moon story isn't just about passive observation. It's also a powerful catalyst for our technological ambitions. Remember those artificial moons we discussed? The ones requiring active station keeping and constant thruster burns? While currently fuel-intensive and exorbitantly expensive, the very concept pushes us to dream bigger. It forces us to innovate in fields like propulsion, energy generation, and autonomous systems. Imagine a future where humanity has mastered the art of spacefaring. We've colonized the Moon, Mars, and perhaps even some of the Jovian and Saturnian moons. What's the next logical step for scientific outposts, deep space observatories, or even self-sustaining habitats? A stable platform orbiting a moon, a custom-built moon. This isn't just science fiction. It's an engineering challenge that, by its very nature, demands revolutionary solutions. Think about the technologies that would need to mature. Ultra-efficient propulsion systems. Beyond chemical rockets, we'd need advanced ion drives, plasma thrusters, or even nascent concepts like gravitational sails that could harness the subtle energy of gravitational gradients to maintain position with the minimal fuel. Autonomous AI systems. A truly self-sustaining artificial moon wouldn't rely on constant human intervention. AI would manage orbital corrections, resource allocation, and system maintenance, learning and adapting to the dynamic gravitational environment. Advanced materials and construction. Building habitats that can withstand the rigors of space, harvest local resources, like lunar regolith for shielding or 3D printing, and create closed-loop life support systems would be paramount. Energy independence, solar arrays, miniature fission reactors, or even radioisotope thermoelectric generators, RTGs, would need to provide reliable long-term power in the deep space environment. The pursuit of an artificial moon, therefore, becomes a microcosm of our broader aspirations for space colonization. It encapsulates the drive to extend humanity's reach, to create new homes and scientific outposts among the stars. It's about taking the elegant, brutal rules of the cosmos and through sheer ingenuity, bending them to our will, not to break them, but to work within their profound elegance to create something new. And this brings us back to the philosophical core of our journey. Why do we find such deep, satisfying peace in understanding the complex interconnectedness of the cosmos? Why does the quest for a moon, whether natural or artificial, resonate so profoundly with our human spirit? Perhaps it's because the universe, in its grand, unfolding drama written in the language of physics, mirrors our own journey of discovery. We start with a simple question, a flicker of curiosity, and it leads us down pathways of intricate knowledge, challenging our assumptions and expanding our horizons. We learn that while some dreams might be impossible in their natural form, the very act of dreaming them pushes us to invent new realities. The moon, in its elusive charm, represents the boundary of what we know and what we can achieve. It's a reminder that the universe, while governed by precise laws, still holds countless secrets, waiting for our persistent gaze and our audacious ideas. It teaches us to appreciate the delicate balance of forces that allow any orbit to exist, transforming what might seem like a simple concept into a breathtaking cosmic ballet. So as we contemplate the moon, whether as a theoretical rarity in an exoplanetary system or a future marvel of human engineering, we're not just exploring space. We're exploring the limits of our knowledge, the depths of our imagination, and the boundless potential of our species. The universe doesn't always give us the answers we expect, but it always gives us answers that are profound, challenging, and ultimately more beautiful than we could have ever imagined. The absence of a moon in our backyard is not a void. It's a canvas, inviting us to paint new possibilities with the brushstrokes of science and the colours of human ingenuity. And that, my friends, is the true magic of dreamy science. The journey continues always. We've journeyed deep into the cosmic ballet, haven't we? We've wrestled with the invisible hand of gravity, explored the delicate dance of orbital mechanics, and stared into the profound elegance and brutal limitations of the cosmos. Our quest for the moon, that celestial nested doll, has led us to a powerful, if somewhat sobering, conclusion. Natural moons, in our solar system at least, appear to be a cosmic impossibility. The universe, in its infinite wisdom and uncompromising efficiency, has decreed that such a configuration is just too unstable, too fleeting, too much of a gravitational tightrope walk to ever truly settle into a long-term self-sustaining existence. The why not for natural moons is a symphony of gravitational tugs and pulls, a cosmic maelstrom where tidal forces, orbital resonances, and the inherent instability of the three-body problem conspire to tear apart any aspiring submoon. It's a testament to the universe's precise, demanding nature, a masterclass in how physical laws sculpt reality, allowing some configurations to flourish and others to be ruthlessly pruned away. This understanding, this refinement of our gravitational models, this enhanced grasp of orbital stability is a treasure in itself, a deep satisfying peace that comes from truly comprehending a fundamental truth of the cosmos. But here's the thing about humanity, about us. When nature says no, we often hear it as a challenge, a whispered, "What if we could?" If the universe, through its natural processes, can't create a moon, what about us? Could we, with our ingenuity, our ever-evolving technology, and our insatiable drive to explore and create, manifest such a celestial marvel? This is where the dream of the artificial moon truly takes flight, transforming from a scientific curiosity into a potential blueprint for our future in space. Imagine, if you will, not just a satellite orbiting a planet or a moon orbiting a planet, but a human-engineered outpost, a meticulously crafted sphere of science and habitation, delicately positioned to orbit another moon. Why would we undertake such a monumental task? The reasons are as varied as they are compelling, painting a vivid picture of humanity's boundless ambition. Firstly, the scientific returns would be immense. An artificial moon would offer an unparalleled platform for observation, a unique vantage point from which to study its host moon with unprecedented detail. Picture an observatory perched on a tiny stable orbit around, say, Jupiter's moon Europa. From this sublunar perch we could map Europa's icy shell with incredible resolution, peer into its suspected subsurface ocean with specialized instruments, and monitor its geological activity, cryovolcanoes, tidal stresses, potential plumes, from an incredibly close distance, without the constant orbital perturbations and communication delays inherent in orbiting Jupiter itself. It would be like having a microscope on a microscope, a nested view of a nested world. Then there's the allure of resources. Our solar system is rich with elements crucial for our expansion: water ice, rare earth minerals, helium-3. Many of these resources are locked away in the moons of gas giants, or even our own moon. An artificial moon could serve as a forward operating base for resource extraction. Imagine a small mining operation, an automated robotic facility, orbiting a large resource-rich moon. It could process materials directly in space, perhaps even manufacturing components or propellants, creating a self-sustaining ecosystem of off-world industry. This isn't just about bringing resources back to Earth. It's about building an independent, self-sufficient space economy, enabling deeper, more ambitious missions, without the astronomical cost of lifting everything from Earth's deep gravity well. And of course, there's habitation, the ultimate frontier. As we dream of multiplanetary civilizations, the concept of a moon offers a tantalizing new paradigm for human settlement. Imagine a rotating habitat generating its own artificial gravity, orbiting a moon like Titan or Ganymede. It would be a true celestial nested doll of human endeavor, a new type of settlement that leverages the unique gravitational and environmental characteristics of a moon's immediate vicinity. It's about finding new homes, new spaces for humanity to thrive, pushing the boundaries of what we consider habitable. A moon could be a stepping stone, an orbital way station, or even a permanent residence, a testament to our ability to adapt and create our own environments in the most challenging cosmic landscapes. But the how of creating such an artificial moon, as we've discussed, is where the real technological marvels come into play. It demands a suite of advancements that currently exist primarily in laboratories or the realm of theoretical physics. First, propulsion. We're talking about more than just conventional chemical rockets. To maintain a delicate, stable orbit against the relentless gravitational perturbations of the host planet and the host moon, an artificial moon would require constant, precise adjustments. This calls for highly efficient, long-duration propulsion systems. Think advanced ion thrusters capable of generating continuous low-thrust forces for years, even decades, with minimal propellant consumption. Or perhaps something even more exotic. Magnetic sails harnessing stellar winds, or even speculative concepts like gravitational sails that could subtly manipulate local space-time, though that veers deeply into the realm of science fiction for now. The key is sustained, precise thrust, not just bursts of power. Next, autonomous AI and machine learning. This isn't just about programming a satellite. It's about creating a truly intelligent entity capable of navigating a complex, dynamic gravitational environment. An artificial moon would need AI sophisticated enough to constantly monitor its orbital parameters, predict gravitational perturbations from multiple bodies, and execute micro-adjustments with pinpoint accuracy, all without direct human intervention for extended periods. It would be a master of the three-body problem, constantly calculating and recalculating its position, its trajectory, and the optimal thrust vectors to maintain its delicate dance. This AI would learn from its environment, adapt to unforeseen shifts, and even perform predictive maintenance on its own systems, ensuring its longevity in the unforgiving vacuum of space. Then there's energy. Powering these continuous thrusters and sophisticated AI systems, along with life support and scientific instruments, would demand robust, long-term energy solutions. While massive solar arrays might suffice in some orbits, a moon in the outer solar system, far from the sun's warmth, would likely require advanced nuclear fission or even fusion reactors. These compact, powerful energy sources would provide the sustained power necessary to keep the artificial moon alive and operational for its entire mission duration, potentially centuries. And finally, material science. An artificial moon would need to be incredibly lightweight yet incredibly robust, capable of withstanding the harsh radiation environments of space, the extreme temperature fluctuations, and the stresses of constant orbital adjustments. We'd need revolutionary materials, perhaps self-healing composites or metamaterials, designed for extreme durability and efficiency. The creation of an artificial moon isn't just about launching a craft. It's about engineering an ecosystem of technology that can thrive in a hostile, dynamic environment. It's a continuous balancing act, a perpetual station-keeping effort that demands vigilance, precision, and an almost symbiotic relationship between human design and autonomous execution. It's the ultimate cosmic tightrope walk, but one we choose to embark on. What does this human ambition tell us about ourselves, about our place in the universe? It speaks volumes about our relentless drive to overcome limitations, to impose a semblance of order, or at least find stability, in a cosmos that often seems indifferent to our desires. It reflects our innate curiosity, our desire not just to observe, but to participate in the grand cosmic drama, to become architects of our own celestial destiny. While natural moons in our solar system remain elusive, the vastness of the cosmos still holds tantalizing, albeit extremely rare possibilities. Perhaps in some distant exoplanetary system, a gas giant with vast, distant and incredibly massive moon, itself orbited by a tiny, perfectly positioned submoon in an exceptionally stable circular orbit might exist. The conditions would have to be so exquisitely precise, so utterly Goldilocks, that their discovery would be a monumental achievement, confirming that nature, given infinite possibilities, can indeed find a way, even if it's the rarest of cosmic gems. Our next generation observatories, peering deeper into the exoplanetary tapestry, might one day catch a glimpse of such a true celestial unicorn. But whether we find them or build them, the journey of asking can moons have their own moons isn't just about the answer. It's about the profound questions it forces us to ask about gravity, stability, and our own place as craters in the cosmos. It's about expanding our scientific and imaginative horizons, pushing the boundaries of what we believe is possible, and fostering a deeper appreciation for the universe's intricate interconnectedness. The quest itself, my friends, is paramount. It's what drives us to look up, to wonder, and to reach for the stars, not just to observe them, but perhaps one day to shape them. We've talked about the universe's elegant, brutal gravitational laws, the cosmic forces that make natural moons a celestial rarity, a whispered impossibility in our solar system. We've explored the relentless tidal forces, the complex three-body problem, and the fleeting nature of orbital stability. But here's the thing about humanity. Where nature presents a wall, we often see a challenge, an invitation to innovate, to build. If we can't find a moon, what if we create one? We briefly touched upon the idea of artificial moons, these magnificent feats of engineering that would defy the cosmic odds. Now, let's truly dive into the why. Why would we embark on such a monumental endeavour? What profound purpose could an artificial moon serve, justifying the immense investment of intellect, resources, and sheer will? Imagine, if you will, the ultimate celestial nested doll, not sculpted by the unseen hand of gravity and time, but meticulously crafted by human ingenuity. This isn't just about proving we can do it. It's about unlocking unprecedented capabilities, pushing the boundaries of what we understand and what we can achieve. An artificial moon, actively maintained in orbit around a larger natural moon, becomes more than a satellite. It becomes a strategic asset, a multi-tool for our expansion into the cosmos. First and foremost, let's consider its role as an unparalleled scientific outpost. Picture a small, precision-engineered observatory, not on the surface of our moon, but orbiting it. From this unique vantage point, a moon could offer an unobstructed view of the parent moon's poles, its far side, its dynamic surface features, providing a continuous, high-resolution stream of data that fixed landers or even orbiters around Earth simply cannot match. It's like having a dedicated scout always circling the mountain you want to climb, sending back real-time topographical maps and weather reports. Think of the geological surveys, the mineral prospecting, the detailed mapping of potential subsurface water ice deposits, all from a stable, elevated platform. But the scientific utility extends far beyond the parent moon. An artificial moon orbiting our moon would offer an extraordinary perspective on Earth itself. Free from atmospheric interference, it could host advanced Earth-observing instruments, monitoring climate change, weather patterns, and global ecosystems with a clarity and consistency that terrestrial satellites might envy. And then there's the deep space view. With the Earth and the parent moon acting as a shield against light and radio interference, a moon could become a dark-side observatory, a radio telescope listening to the whispers of the early universe, or a gravitational wave detector precisely positioned to catch the ripples in space-time. It's a cosmic research station on steroids, offering a kaleidoscope of observational possibilities from a truly unique perch in our solar system. We could study cosmic rays, solar flares, and the subtle interactions of our solar system's magnetic fields with a granularity we've only dreamed of. Beyond observation, an artificial moon opens up entirely new avenues for in situ resource utilization, ISRU, and space-based industry. Our natural moon, for instance, is rich in valuable resources: helium-3, a potential fuel for clean fusion power, rare earth elements, and critically, water ice in its permanently shadowed craters, essential for life support and propellant. A moon could serve as a forward operating base for robotic mining operations on the lunar surface. Imagine drones descending from the moon, collecting samples, processing them, and then returning the refined materials to the orbiting station for further refinement or transfer. It's a celestial construction yard, a manufacturing hub leveraging the unique advantages of microgravity and vacuum. We could fabricate components for larger space structures, refine propellants for missions further out into the solar system, or even build entire spacecraft in an environment perfectly suited for it, free from the constraints of Earth's gravity and atmosphere. This isn't just about extracting resources, it's about building an off-world economy, a self-sustaining ecosystem of industry and innovation. And let's not forget the strategic advantage. An artificial moon could act as a communication relay station, a vital node in an expanding interplanetary network. As humanity ventures further to Mars and beyond, reliable communication will be paramount. A moon strategically placed could ensure continuous contact with deep space missions, providing redundancy and robustness to our interstellar conversations. It's a cosmic lighthouse, guiding our messages across the vast distances of space. Perhaps the most compelling vision, however, is the role an artificial moon could play in all future human habitats and colonization. As we look to establish permanent outposts on the Moon and eventually Mars, these orbiting stations could serve as critical stepping stones. They could be orbital way stations for crew rotation, supply depots, or even temporary refuges. Imagine a moon designed as a closed-loop ecosystem, a testbed for sustainable living in space, where we learn to grow food, recycle water, and manage waste in a truly self-sufficient manner. These artificial worlds, though small, could become humanity's first true off-world settlements, laboratories for future colonization, preparing us for the ultimate leap to other planets. They represent a tangible step towards becoming a multiplanetary species, a future where our destiny isn't confined to a single world. Of course, the challenges we discussed earlier, the need for ultra-efficient propulsion for constant active station keeping, autonomous AI for orbital management, robust energy sources, and innovative materials, don't magically disappear. In fact, they are amplified when we consider building and maintaining such a complex structure. But here's where human ingenuity truly shines. We are talking about developing entirely new classes of ion thrusters that sip fuel over decades, AI systems capable of predicting and correcting orbital perturbations with exquisite precision, and materials that can withstand the harsh radiation environment of space while remaining lightweight and durable. This isn't just about building a moon. It's about pioneering the next generation of space technology, pushing the very boundaries of engineering and robotics. It's a grand challenge that would galvanize scientists and engineers across the globe, inspiring breakthroughs that ripple into countless other fields. So when we look up at the familiar silver orb hanging serenely in our night sky, and we ponder the impossibility of a natural moon, we also see a canvas for our ambition. The absence of natural moons reveals profound truths about the universe's elegant yet brutal gravitational laws. But the human quest to find, or failing that, to build them, reflects an even deeper truth about ourselves. Our insatiable drive for understanding, for creation, for pushing the limits of what is possible. It's a testament to our relentless curiosity, our desire to not just observe the cosmic choreography, but to become participants in it, perhaps even choreographers ourselves. This journey, this intellectual expedition into the mechanics of our universe, reminds us that the stories written in the language of physics are not just tales of what is, but also of what could be. We've traversed the vastness of cosmic possibility, from the theoretical Goldilocks scenarios in distant exoplanetary systems to the cutting edge of human engineering right here at home. We've seen that the universe, in its raw, unadorned state, might not readily offer us moonmoons, but it does offer us the profound satisfaction of understanding why. And perhaps, just perhaps, it offers us the opportunity to add our own intricate human-designed nested doll to its grand unfolding drama. We've talked about the how of building artificial moonmoons, the technologies needed to defy gravity's elegant brutality. But what does it truly mean for us as a species to undertake such an endeavour? What are the broader implications, the ethical considerations, the philosophical shifts that come with becoming creators of celestial bodies, even miniature ones? Join us next time on Dreamy Science as we explore the profound impact of humanity's ambition and what it truly means to shape our cosmic destiny. We've journeyed far, haven't we? From a simple, almost whimsical question, can moons have their own moons? We've spiraled through the intricate dance of celestial mechanics, wrestled with the formidable equations of gravity, and peered into the tantalizing possibilities of both nature and human ingenuity. Our expedition has taken us from the familiar silver orb hanging serenely in our night sky to the unimaginable depths of exoplanetary systems, pushing the boundaries of what we thought we knew about the cosmos. It was a question born of childlike wonder, perhaps posed on a clear night under a canopy of stars, a gentle whisper that blossomed into a full-fledged scientific odyssey. We, as a collective consciousness, felt that initial spark of curiosity, a shared human impulse to dissect the universe's grand design. As we stand here at the culmination of this particular segment of our dreamy science exploration, it's worth reflecting on the vast terrain we've covered, the intellectual landscapes we've traversed. We began with that delightful concept, the moonmoon, a cosmic nested doll, a celestial matryoshka, that captured our imagination with its elegant simplicity. But immediately we ran headlong into the universe's uncompromising efficiency, its elegant but unyielding rules. We uncovered the invisible hand of the Hill sphere, that delicate, often ruthless, bubble of gravitational influence that defines a moon's personal space, its dominion. We saw it not just as an abstract boundary, but as a tangible force, a gravitational fence line dictating what can stay and what must go. We felt the relentless tug of tidal forces, stretching and pulling at the very fabric of celestial bodies, threatening to rip apart any would-be submoon with an almost casual cosmic violence. Imagine the slow, inexorable deformation, the internal stresses building until the very integrity of a body is compromised. And we grappled with the inherent chaos of the three-body problem, a cosmic ballet so complex, so intrinsically unpredictable, that stable long-term formations become a statistical impossibility under most circumstances. It was like trying to choreograph a perfect dance with three partners, each pulling in a different direction, their movements influencing each other in an infinite recursive loop. What we discovered, with a mix of wonder and a touch of awe, is that the universe isn't just a playground, it's a meticulously engineered machine. Its laws are not suggestions, they are absolute, elegant, and brutally efficient. The why not of natural moonmoons in our solar system isn't a failure of imagination on the universe's part, but rather a profound revelation about the deep interconnected principles that govern every celestial body. It's a testament to the elegant simplicity and unforgiving nature of orbital mechanics, a symphony of gravity where every note must be in perfect harmony for stability to endure. We might wish for a moon with its own tiny companion, a miniature satellite orbiting a larger one. But the universe, in its grand wisdom, doesn't cater to our aesthetic preferences. It operates on principles of energy minimization and stability, often sacrificing complexity for enduring order. But as we peeled back these layers of cosmic impossibility, as the universe seemed to whisper a firm no to our initial query, we also encountered the boundless audacity of human ambition. If nature, in its infinite wisdom, largely says no to natural moonmoons, what about us? Could we, with our ingenuity and relentless drive, become the architects of our own celestial destiny? The concept of artificial moonmoons emerged not as a defiance of physics, a futile attempt to break its laws, but as a testament to our ability to work with physics, to bend its rules through technological mastery, to sculpt new realities within its strictures. We envision them not just as engineering marvels, but as unparalleled scientific outposts, forward operating bases for in situ resource utilization, crucial communication relays, and even new paradigms for human habitats. Imagine a tiny gleaming sphere, perfectly positioned in orbit around our own moon, its surface bristling with scientific instruments, silently observing the lunar surface below, or acting as a staging ground for missions deeper into the solar system. Perhaps it would be a vibrant, self-sustaining habitat, a miniature world providing a new perspective on our place in the cosmos, a beacon of human persistence. The technological demands, we acknowledged, are formidable. Ultra-efficient propulsion systems capable of active station keeping, constantly making minute adjustments to maintain a stable orbit. Advanced autonomous AI to manage the intricate ballet of orbital maintenance. A digital conductor orchestrating the celestial dance. Robust and sustainable energy sources, perhaps miniature fusion reactors or vast solar arrays, to power these distant outposts for decades or centuries, and revolutionary materials science to construct these cosmic wonders, materials that are lightweight yet incredibly strong, capable of withstanding the harsh radiation and extreme temperatures of space. These aren't just hurdles, they are catalysts, driving us to innovate, to push the very limits of engineering and design. The pursuit of artificial moonmoons becomes a powerful engine for groundbreaking advancements that will benefit all of space exploration, regardless of whether a moonmoon ever takes flight. The very act of striving for such a complex goal forces us to invent solutions that will inevitably find applications in other, perhaps more immediate space endeavors. And here's the thing, the profound truth that underlies this entire journey. The real treasure isn't just the answer to can moons have their own moons. The real treasure is the journey itself. It's the knowledge we've gained, the questions we've learned to ask, and the deeper understanding we've cultivated about the universe's intricate workings. Even if a natural moon remains an elusive phantom in our own cosmic neighborhood, a beautiful but unattainable dream, and even if artificial ones are still decades or centuries away from becoming reality, the intellectual exercise of exploring their possibility has illuminated fundamental truths about gravity, stability, and the very fabric of space-time. It has refined our mental models of how the universe truly operates, stripping away naive assumptions and replacing them with a more nuanced, sophisticated understanding. This quest refines our understanding of what makes a celestial body stable, what allows it to endure in the relentless push and pull of cosmic forces. It teaches us about the delicate balance required for any multi-body system, a lesson that extends far beyond just moonmoons to encompass planets, stars, and galaxies. It helps us understand the conditions for habitability, not just on planets, but on moons orbiting those planets, and even on hypothetical moons orbiting those moons. We learn to appreciate the brutal elegance of the cosmos, not as a barrier to our dreams, but as a challenge that hones our intellect and expands our perspective. It's a humbling realization, recognizing the universe's indifference, yet finding immense beauty and profound lessons within that indifference. Now, let's project ourselves forward, beyond our own solar system. Imagine the next generation of powerful telescopes, like the James Webb Space Telescope's future successors, peering into the atmospheres and even the surfaces of distant exoplanets and exomoons. Armed with the insights we've gathered about moon-moon stability, we gain a new lens through which to interpret their observations. We know what to look for, the specific orbital parameters, the mass ratios, the distances that might just allow for a stable exomoon-moon. We understand the Goldilocks conditions, a massive primary exomoon, a tiny close submoon, perfectly circular orbits, all distant enough from their parent gas giant to escape its overwhelming gravitational influence. The search becomes less about blind luck and more about targeted observation, guided by the hard-won wisdom of celestial mechanics. It's like having a cosmic filter, sifting through the immense data, knowing exactly what improbable signatures to seek out. This isn't just abstract physics, it's a practical framework for future astrobiology. If life can arise and vegetate on an exomoon, could it also, however improbably, find a niche on an exomoon? Perhaps in a tiny sheltered environment far from the chaotic gravitational tugs, microbial life could flourish, sustained by exotic energy sources. The conditions we've explored, the limitations we've identified, become crucial filters in the vast sea of exoplanetary data. Our understanding of why moon-moons are so rare in our own system gives us a template for predicting their rarity, or perhaps even their existence, in others. It transforms the search for habitable worlds into an even more nuanced and sophisticated endeavour, broadening our definition of where life might conceivably cling to existence. Ultimately, this entire exploration is a testament to the enduring power of human curiosity. We started with a "what if?", a simple, innocent query, and that single spark ignited a journey through physics, engineering, and philosophy. It led us to confront the universe's uncompromising laws, to dream of overcoming them, and to appreciate the profound beauty in both the yes and the no that the cosmos offers. It is a dialogue between our hopeful imagination and the universe's cold, hard truths, a conversation that always leaves us richer for having engaged in it. We, as a species, are driven by this relentless pursuit of knowledge. We gaze at the night sky not just to admire its beauty, but to unravel its secrets. We ask why and how, and in doing so we not only expand our understanding of the universe, but also deepen our understanding of ourselves, our limitations, our potential, our boundless capacity for wonder. This shared wonder, this intellectual adventure we've embarked upon together, is perhaps the most human endeavour of all. It connects us, inspires us, and constantly reminds us that the universe is an endless source of fascination, waiting for us to ask the next question, to embark on the next dreamy science journey. So, while the natural moon remains an elusive celestial dream in our solar system, a poetic fantasy that physics currently denies us, the insights gained from chasing that dream are anything but ephemeral. They are concrete, invaluable, and foundational. They are the true gems unearthed on this extraordinary expedition, shining with the light of newly acquired wisdom. And as we conclude this chapter, remember that the universe, in its infinite complexity, always holds more secrets, more wonders, more questions waiting to be asked. The journey of discovery, my friends, is truly endless, and it is glorious.